Continuation of our review for the lab final. So the next lab was lab 4, and that was the lab where we talked about elements and then electronic configuration, and we were drawing those orbital diagrams. We were doing the 1s2, 2s2, that kind of stuff. The main things you'll probably need to know here are the properties of metal and the properties of a non-metal, right? And so remember, I've told you to think about copper as your prototypical metal because you're familiar with a lot of the properties of copper. But metals are good conductors of heat. That's why they used to, or sometimes still do, use copper for cooking pans because they conduct heat well. Metals are also good conductors of electricity. That's why you use copper for wires. And they're malleable and ductile, which means you can hammer them into pennies, and you can stretch them into wires, or hammer them into sheets like flat pennies, or stretch them into wires like copper wires, and they tend to be solids, right? Most of the metals are solid except for mercury, which is a liquid. So for the properties of nonmetals, they're kind of the opposite, right? They're brittle, you can't shape them very well, they're not good conductors of heat, and they're not good conductors of electricity. So you should be able to recognize if something is a metal or a non-metal based on a description of its properties. You should also be familiar with the periodic table from this lecture. So and this is a pretty basic skill, so I don't think you'll have any problem with it, but you should be able to look at an element symbol and go find its name from your periodic table. So that shouldn't be very difficult. All right, so next lab up was lab 5, and that was our molecular modeling. So we talked about the dimensional shapes that these molecules make, right? They want to take the shape that separates the electron pairs as far from each other as possible, because those electrons are negatively charged and they repel each other. So one of the first things we discussed were Lewis dot structures. And that's when we drew an element's name, and then we just put the number of valence electrons around it as dots, right? So if we had something like sodium is in group 1, so everybody in group 1 of our periodic table, group 1, first group, has 1 valence electron, so sodium would look like this with a dot, right? And remember, the valence electrons are the ones that are taking place in these chemical reactions, and they're the ones that are going together to form bonds. Right, so that would be a Lewis dot structure of an element. And we could pick another element like, say fluorine, and fluorine is a halogen, so it's in group 7, so it has 7 valence electrons. So we'd put dots around 2 on each side until we have our 7 valence electrons. So that'd be the Lewis dot structure for fluorine. So the other thing you could have, so these would be elements here. You could also have the Lewis dot structure of an ion, right? So an ion is just an atom that has either gained or lost electrons and now is charged, right? So if we lose electrons, then we become positively charged and become a cation. If we gain electrons, we become negatively charged and become anions. So right, sodium is in group 1, so when it forms an ion, it's going to be Na+. Fluorine is in group 7. It's going to gain an electron and have a negative charge when it becomes an ion. So if we wanted to draw the Lewis structure of an ion, we'd have to take into account that it lost or gained those electrons. So sodium, to become sodium+, has lost that electron, so he would have no valence electrons. But fluorine gained an extra electron, so if we were drawing its Lewis structure, then it would have an extra electron out there on the outside. So once we learned how to draw these simple Lewis structures of just elements and ions, then we moved on to doing Lewis dot structures of actual molecules, right? And so if you look at the handout that should be online about the reviewing, the examples it gives you are Ni3, right? So if we want to draw the Lewis structure for nitrogen triiodide, first thing we have to do is find out how many valence electrons we have, right? So nitrogen has 5 valence electrons, and then we have 3 iodine, N, 1 N, 3 I's. Each of those iodine is going to have 7 valence electrons, right? So that left us with 26 electrons. And then our next step was to put some guy in the center and connect them with lines. So we put our nitrogen in the center. We connect it with these 3 iodine. That represents 2, 2, 2. So that's 6 shared electrons. So we have another 20 electrons that we're going to distribute to try to make everybody think they have 8 electrons. So our next step was to put them on the terminal atoms, which are the ones not in the center. So we could put over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So those each could take 6 more, so we still have 2 pairs of electrons, or 2 electrons left. Then our next step was to put them on the central atom, so we could put a pair of electrons up here. And now we've given away all of our electrons, so we have 0 electrons left. And then to make sure our structure is correct, we have to count how many valence electrons everybody sees. So this iodine sees 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Nitrogen sees 8. So everybody's happy with that structure. So that would be the correct structure. And if we wanted to draw it, in 3-dimensional shape, we had to have something like this, where we'd have a non-bonding pair up here and 1 iodine in the plane, and then 1 iodine sticking out towards you and 1 then behind the blackboard. So then we would use our chart that you'll have, your VSEPR chart, and look at the structure of the electron pairs. So these 4 pairs would all be in a tetrahedral shape. So the shape of the electron pairs would be tetrahedral, and if we wanted to look at the shape of the molecule, we ignore these, and we see we have a trigonal pyramidal shape. So that's how you would do a Lewis structure here. And if you're doing these, I would hold off on double and triple bonds till the end and make sure that I actually need those. So as another quick example, if we had H2S, we're going to first count our valence electrons. So we have 2 hydrogen, they each have 1. Sulfur has 6 because it's in group 6, so we have 8 electrons to share. We're going to put the sulfur in the middle, connect the 2 hydrogen like this. So we've used 2, 4. So we have 4 more electrons to share. Hydrogen can only take 2, so no more electrons on the terminal atoms. We have to come back to the central atom. So we can put 2 below sulfur and 2 above sulfur. That leaves us with 0 electron pairs to share. Hydrogen sees 2, so it's happy. Sulfur sees 2, 4, 6, 8, so it's happy. So that would be our correct Lewis structure. Now if we wanted to look at the 3-dimensional shape, we'd have this shape here, just kind of like water, where we'd have a pair of electrons sticking out of the board and a non-bonding pair behind the board. So again, the shape of the electron pairs is tetrahedral, but our actual molecule, if we ignore those, would be bent. All right, I forgot to do this on the last one, but this would be AB2E2. We have 2 atoms bound, and we have 2 electron pairs. Next lab was lab 6, chemical nomenclature. So that was learning how to name these different compounds. And remember, there were 3 main types that we focused on: type 1, type 2, and type 3. In type 1, the metal is a metal that always forms the same charge. In type 2, the metal is a metal that can form a variable charge. And type 3 is between 2 non-metals. So let's look at a couple of quick examples here. If we have a sodium chloride, sodium is in group 1, so it's a metal that always forms a +1 charge. So it's a type 1 compound. So what we do is the metal keeps its name, and it's named first, so this would become sodium. And then the nonmetal chlorine changes the ending of its name to IDE, so it would become sodium chloride. And this is what we call a binary compound. So you should know a binary compound is when you just have 2 different elements put together, so that would be binary. The other thing we saw were what were called ternary compounds, and those had a polyatomic ion in there, and so they had more than 2 elements. So if we look at this next next compound here, you can see we have sodium, nitrogen, and oxygen. So it's not binary, it's ternary. And once you see that it's ternary, then you need to go to your table of polyatomic ions and find the name of this ion here, this NO3. So again, this is type 1, so sodium just keeps his name. So this would be sodium. And then from your polyatomic ion table, you should be able to find the NO3 minus is called nitrate. So that would be sodium nitrate. And, you know, that's how you would name a type 1 compound. So type 2 compounds, the metal can form a variable charge. So we have to give the state of the charge with Roman numerals. So the example shown here, iron 2 chloride, that tells us that the iron has a +2 charge. All right, so our iron has a 2+ charge. Chlorine is in group 7, so it's always going to form a -1 charge. So the trick here is to figure out how those go together to form a compound. So you can do your cross multiplying. That means you need 2 chlorine, one of these. So if we were going this direction, this would be FeCl2. That would be iron 2 chloride. Here we have copper with chlorine. Copper is a metal that always forms a variable charge, so we need to put in Roman numerals what its charge is. And the way we figure that out is that chlorine is always going to have a -1 charge, so we need to figure out what charge on the copper balances that -1, and that would have to be a +1. So this becomes copper 1 chloride. So remember the Roman numeral tells you the charge on the element or the metal, not how many of those you have. Type 3 is when you have 2 nonmetals, right? So 2 things from the upper right side of your periodic table. These are not ionic compounds, these are the covalent compounds. And then from your table that I gave you, you just use those prefixes to say how many of each one there is. So here we have 1 copper and 2 oxygen, so this would be carbon. And then di for 2, dioxide. If we have something like dinitrogen hexide, that's saying 2 nitrogen, so we'd have N2 and 6 oxygen, so O6, N2O6. So make sure you can name those different types of compounds.